Okay. Good morning, everybody. Thank you so much for your patience. We were just getting the Spanish interpreters all set up for success. My name is Dana Lehman. I work for the town of Crested Butte. I'm the sustainability coordinator for the town. I'm working with what we're calling the Gunnison Valley Building Code Collaborative, which is a group of municipalities. So that's the town of Crested Butte, Mount Crested Butte, the city of Gunnison, and Gunnison County, to present to you today through a grant from the Colorado Energy Office, the Gunnison Valley Building Code Energy Efficiency for Builders series. This series is an educational opportunity to help builders like you, contractors who serve our valley, to understand what's going on with our building code in the Gunnison Valley. Things have changed over the last few years, and several of the towns have changed their building code. And I know that folks have had a lot of questions. There are many resources out there for builders, but we wanted to deliver something that was more relevant to our local building codes. So I'm going to introduce Robby in just a moment. I think maybe some of you might know him already, but we're really glad to have him here today to walk us through the technical building code information that hopefully is helpful to all of you. If anybody needs it, we do have Spanish interpreters on the call. And you can tune into the Spanish channel by clicking on the interpretation button at the bottom of your screen. Please send us a message or feel free to tune into that channel if you do need live Spanish interpretation. Robby, if you could maybe change the next slide about the scholarship, and then I'll let you take it away. Thank you. So as part of this Colorado Energy Office grant, Gunnison County is also offering an energy efficiency professional scholarship program. That program is available to any contractor that is looking for an energy efficiency certification, training. It even funds equipment. So you can visit the Gunnison County website to find that scholarship program. It usually comes up on a Google search pretty easily, and you can apply for up to $2,500 for any of your certifications equipment. It is a really broad program and lots of things qualify. So please don't hesitate to send us an email. Crystal Lambert is the employee at the county who is managing that. So send her an email, ask questions. This money is meant to be distributed, and we really want to see people apply to this program. So please feel welcome to apply there. With that, I want to introduce Robby Schwarz. He works for BuildTANK Inc. He's a building code and builder extraordinaire. So I'm going to let him take it away. Thanks, Robby.
Great. Yeah, thank you so much for having me today. And today we'll be talking about the 2021 IECC and kind of specifically the compliance pathways there. I'm going to leave my video up, but you might see the side of my head because I have two screens going here occasionally. So just try to concentrate on the slides. Today we'll kind of be concentrating on Chapter 4 because Chapter 4 is where in the residential energy code is where the cost and flexibility and the compliance paths are demonstrated there. We'll talk a bit about the differences between mandatory and other requirements because the language has changed a bit in the code since the 2018 and earlier versions. And then we'll talk about the specific compliance options that you have, the prescriptive, the UA trade-off, total building performance, and energy rating index pathways there. But to start way back in 2012, when the 2012 IECC was created, there was kind of this apocalyptic feeling. And because it was the first code where blower door testing was a mandatory requirement. And code officials around the country really didn't understand how airtight their houses actually were, and if they could get blower door testing to actually happen in all those jurisdictions around the country. And that's really one of the reasons why the scholarship program's been created, is because we need to continue to build the infrastructure of people who can do the testing and kind of assistance in code compliance work as we move forward. As we move into the 2021 IECC, we kind of have this additional apocalyptic moment happening, because really between the 2012 and the 2018 IECC, not a lot happened out there in the code world. But in the 2021, we got an increase in efficiency that was pretty dramatic there. So I'm going to take you to this chart, and we're going to use the 2006 as the reference point here. And you can see that the move from the 2006 IECC to the 2009 IECC, we got about an 8% increase in efficiency. And how that's determined is that the Department of Energy does an energy code determination at the end of the code development cycle to determine how much forward progress we've made in terms of gaining more efficiency. However, the way that they do that is they look at the letter of the code, not how the code is actually adopted in different municipalities. So if you were to adopt the code without any amendments and implement it and enforce it without any amendments, you would get about an 8% increase from the 2006 to the 2009 IECC. Now, that happened really on the back of increased R values and U values in the code requirements there. And you can see from the 2009 to the 2012 IECC, we got about a 20% increase in efficiency. And that came on the back of the blower door requirement. So we see that a portion of the energy moves in and out of our houses by conduction, or energy moving directly through the building assemblies and materials in our houses, and maybe even a larger portion of the energy that's moving in and out of our houses is moving with air. And so air is a great transport mechanism for energy and moisture and pollutants and whatnot. So we have to gain control and predictability of that airflow in and out of our houses. And that's one of the big reasons why blower door testing was added to the code in the 2012 IECC. Or it wasn't really added, it was required before, or it was an optional requirement before. For some reason, before the 2012 IECC, people thought I could look at a house and just kind of tell if it was airtight or not. And obviously that's not true. You get
Obviamente esto
O
no es
no, pero
cierto.
eso no es cierto. No, al hacer la
Recibiendo tu
prueba,
prueba,
no es
sino
lo que
lo
se
que esperas.
espera.
Así es que
En el
en el 2 hicimos
2012 se
este
hizo este
cambio.
cambio.
Podemos
Se
ver la
puede ver.
2015, where there was no increase in efficiency, and the 2018, where there's about a
El
1.
Y el
2018, donde había como
2018
un por
hubo
ciento
una
de
eficiencia del
eficiencia.
1%.
Community really was hearing what was happening out in the field out there, and wanted to give jurisdictions time to catch up with some of these changes that were happening. That time slot ended, and we have the 2021 IECC, where we got about a 10% increase in efficiencies. So they've really kind of almost maxed out what they can get with increasing R values and U values, although that was increased a little bit in the 2021 IECC. We haven't necessarily maxed out in what we can achieve by creating more airtight houses, but they added an additional efficiency package to the equation in the 2021 IECC, and that's how we got that. That's the primary reason how we got that increase in efficiency there in the 2021 IECC. So that kind of gives us a progression of how the codes have been developed over time. The 2024 IECC is just about to be published. We don't have a determination yet from the Department of Energy, but I would be surprised if it's up in that 10% range there. We'll have to wait and see where it comes out to. Now, the authorities having jurisdiction in the Gunnison Valley have a lot to do besides just looking at energy efficiency there. They're looking at permitting, but also residential buildings and commercial buildings. They have to look at electrical, mechanical issues, fire, all kinds of inspections for plumbing and whatnot beyond energy there. So the Department of Energy actually created kind of a guide here for how to successfully adopt and enforce the energy codes here. And some of the things that they talk about in these top 10 reasons is, first, know which energy code you're working at. As we're transitioning from one code to another code, you usually have some type of grace period where your house might still be on the old code, but they might be inspecting and kind of getting ready for the new code. So they might be confusing some things. So if you are certain that your house is permitted under a specific code, it kind of makes the process go a lot more smoothly there. Understand the compliance pathway that you're using. You have to propose how you're going to build that house, and that proposed process is the compliance pathway that you're using, that we're going to be talking about today here. Know all the requirements. In the 2021 IECC, we're going to see that the old kind of structure of mandatory requirements and prescriptive requirements has gone away. Basically, everything is a requirement. Therefore, everything is basically mandatory there. Design and build to meet those requirements, obviously. Document the design and the plans and specifications. The code does have a lot of requirements to include documentation and include diagrams of how specific assemblies are going together. And we're going to get into that in our next session in more depth there. Construct the building to meet those plans and specifications. And then you have to document the as-built building, because as we know, things change during the construction process there. And those changes need to be documented to ensure that those changes continue to meet the requirements of the code. Ensure that the as-built building performs and operates as intended. That gets into some of the testing that's required, some of the quote-unquote commissioning of our houses, the blower door testing, the duct leakage testing, and now in the 2021 IECC, ventilation measurements is a requirement. And then you need to provide code compliance documentation. That documentation comes from not only providing your plan set for it, but you have compliance documents that are required throughout the process. And we'll talk about some of those today. And then ultimately, things are getting complex out there. So don't hesitate to get assistance. There are a lot of folks out there that act as approved third parties for different jurisdictions that can help you through the inspection process, the design process. And then there are other consultants out there, energy raters and other energy consultants that can help. Their passive house, if you're going that far, has consultants and all those types of things. So how do we start incorporating that into the code? We start with Chapter 1 of the IECC, and we see that the code is asking us to look at the construction documents and develop these construction documents to be turned in for permitting. These construction documents are supposed to be created by registered design professionals, but that kind of leaves out this other category of documents that have to be turned into different jurisdictions, which is the compliance documents. And it's not a requirement that a registered design professional turn in these compliance documents. So when we're talking about the construction documents, obviously you have all of these different things that have to be incorporated into those compliance documents, like the electrical plans and the mechanical drawings and those types of things. But there are also the compliance documents that have to be turned in for permitting. And then you also have to turn in some of the compliance documents to actually achieve and get your certificate of occupancy. And one example of a compliance document would be a blower door test report, for example, that needs to be turned in to demonstrate that the house had the test and that it passed the test there. So compliance documents kind of fall into step 9 of that DOE pathway that I was showing you there. It's a crucial step in ensuring that the energy code compliance is actually happening. And a lot of times you have to submit those proper compliance documents to get your permit there. And then those documents need to be reviewed actually by the code jurisdiction. So if you have your paperwork in a row, it often goes through the jurisdiction in a much more faster and smoother pathway there. And then here are some types of the compliance documents that we're talking about. A lot of them have to go specifically with the compliance pathways that we're talking about them, but a lot of them are also revolving around the testing and inspections that happen throughout the construction process there. Next, we're going to move into chapter 4 here and talk about the building thermal envelope. So obviously the energy code is hugely revolving around protecting the building thermal envelope. So we have to have a clear understanding of the building thermal envelope. And the way that the code defines or creates the building thermal envelope is through the definitions section, which is in chapter 2, all the definitions. And we see in this definition here that the building thermal envelope is an assembly of things. And that assembly of things is creating this boundary condition that separates conditioned space from unconditioned space. And we are asked, and going back to chapter 1, we are asked to define that building thermal envelope on our construction documents by doing some type of depiction. Usually it's done on a sectional drawing. And we often think about the building thermal envelope as, again, that boundary condition that's separating conditioned space from unconditioned space, but it's made up of some specific assemblies. Often we think about it as our air control layer and our thermal control layer in alignment with each other all the way around the house there. And we see that the air barrier is also defined in the energy code, and it's also defined as a assembly of things that restrict and prevent the passage of air through the building thermal envelope. So we know through that definition that those assemblies are adjacent to each other, and that the air barrier is it's one of the assemblies that's part of the building thermal envelope. So when we break it down into its lower or smaller increments there, we see we have an air barrier system and we have a thermal barrier system. And we have, in essence, belts and suspenders approach to be able to control thermal flow through the building as well as air through the building. So we've got, in some cases, you can think of it as we've got an air barrier, a primary air barrier on the outside. We have a primary air barrier on the inside of our building. And then we have the thermal control layer kind of sandwiched in between the two of those things. The other thing that the definitions point out and a lot of the code requirements point out is that we have a combination of these materials again, but they have to be continuous all the way around the building. So we have to have that continuity there so that we can have clear protection or clear ability to retard the flow of energy through the building envelope and control the airflow through the building envelope. So continuity of that thermal barrier and control layer is crucial in the codes. We need alignment with the thermal envelope and the air barrier systems so that we have that barrier there. And again, the code is really approaching things as a belts and suspenders approach, where we have a primary air barrier on the interior of the house, which would be the continuity of our drywall all the way around the inside of the building. We have a primary exterior air barrier on the outside, which generally is the continuity of our exterior sheathing out there. And we need the continuity of both of those things. And you might be thinking as a builder, well, you know, my air barrier is my zip system, and it's on the outside of my house, and my air barrier is just that one plane on the exterior of the house. And yeah, you can say that your air barrier is on the exterior of the house. It's my zip system, or it's my weather resistant barrier because I've installed that in such a way that it's also an air barrier. But it doesn't negate the fact that the interior side and the assembly approach is also contributing to the air tightness and performance of the insulation of that house. So again, I think if we think about it as a belts and suspenders approach, and we think about it as a system or assembly of things that are coming together to create that boundary condition, we're going to be more successful because we're not going to just concentrate on one piece of the assembly. We're going to concentrate on the entirety of the assembly as we build it to make it work there. So we want to make sure, again, that we have the continuity of the air control layer and the thermal control layer of our houses. And a prominent building science in our community came up with this red line test, which is mirrored in the requirement of the code to depict the building thermal envelope on the construction documents. And the idea of the red line test is that you put pen to paper and you draw that line around the perimeter of the house or around different sectional drawings of the house. And if you have to pull that pen off the paper, there's probably something going on with the assembly that you need to look at in a little bit more depth there to understand how I'm going to get the continuity of my air and thermal control layer around that particular location. And what you'll see when plan sets are turned in here is that depiction kind of focuses us on areas where different assemblies are coming together. So you can see circles around where the roof assembly is meeting the wall assembly, or where the wall assembly is meeting the foundation, or where floor systems are coming together. All those connection points are generally areas where we're going to get elevated leakage, air leakage happening in our houses, and also potentially elevated thermal bypasses happening in our houses. And those are things, obviously, that the code is trying to work against here. So we want to depict our building on thermal envelope on the construction documents, and we're starting to see construction documents that have a true energy page that's associated. So it's beyond just the mechanical design. It's showing the depiction of the building thermal envelope. It's showing the air sealing details that are required by the code. It's showing the R values and U values that are associated with it. And then in this case, on the right-hand side here, it actually put in some of the code requirements for air barriers, air sealing, and insulation installation, which we'll primarily be talking about next time there. So you might start seeing some of these documents show up in the field, which are all meant to help get this knowledge that's in the code book into the field, into the hands of the people that are actually building the houses, to help them understand what's required and how to do things. And a lot of things with regards to the energy code are all about how things are sequenced and who's responsible, which trade partner is responsible for those different things. Okay, so starting with that kind of overall background, let's dive into the compliance pathways. And the compliance pathways are pathways through kind of this maze of energy code. And we're trying to figure out where the flexibility and ability to kind of do things the way that we want to do them, but also in alignment with the energy code. So you're going to see that different compliance pathways have different levels of flexibility built into them. So we have the compliance pathways that include the prescriptive compliance pathway, which is including the U and R value tables and the area weighted trade-off approach. We have the simulated building performance approach, the energy rating index approach, and regardless of which compliance pathway you use, now you also have additional energy requirements that you have to abide by. So one of the things that we need to delve into before we really get into the compliance pathways is a recognition that the word mandatory has been taken out of the code. The word mandatory was always in regards to requirements of the code that you had to implement, I guess, during the construction of the home, regardless of the compliance pathway you had. But there was confusion because there were prescriptive requirements and there were mandatory requirements, and it turned out that parts of both of those needed to be done regardless of the compliance pathway, not just some of them. So what the code development group did was that they broke out specifically for the performance compliance approaches, which is utilizing energy modeling to demonstrate compliance with the code. They broke out in these tables the actual mandatory requirements that had to be done for that particular section there. So they're not, again, called mandatory, but they're called requirements, and requirements are required, and therefore, in essence, they're mandatory there. And to give you an example of why this happened, if you look here, hopefully you can see my cursor here, you can see this R402.2.3 section for attic eave baffles. Now, attic eave baffles need to be installed when you're installing a ventilated roof assembly, a ventilated attic assembly there. And that used to be in the section that was labeled as prescriptive. So some joker said, I'm building under the performance approach, and therefore I don't have to install attic eave baffles, and I'm going to save some money. And obviously the building science doesn't promote that, and the code doesn't promote bad building science. So we realized that the language mandatory was kind of distracting, I guess. And what we really need to realize is that there are requirements, and all the requirements need to be looked at. And if you're doing a specific detail, you might have to abide by that requirement. And if you aren't doing that detail, well, obviously you don't have to abide by that requirement there. But these tables give us a better guideline when we're using a non-prescriptive compliance approach to understand what we need to be looking at in the codes. It also leads to kind of some of this terminology changes here. So to understand requirements, requirements are basically mandatory. They're meant items that could not be traded off. And we'll get into what trade-offs actually mean here in a second. Requirements must be met by every compliance pathway. They're found in the specific sections and or tables of the code. So you need to understand the code and know where to look for those requirements. And they're often, requirements are generally based about installation instructions, how to install something. So you might have a requirement or a section of the code that's kind of mixing R values and U values with how you install that R value and U value. And in that case, you need to break those things apart so that you can focus on the installation instruction, because the R value instruction isn't necessarily mandatory. The R value part of that requirement could give you some flexibility in if you're using a performance approach to trade off that R value, whereas the requirement for how you install it still is maintained there. And we'll get into that in more depth as we move through this series here. Now, prescriptive requirements can't be traded off in most cases unless the trade-off is spelled out specifically in the language of the code. The other way that we do trade-offs is through energy modeling, and that's in this performance compliance approach that I'll be showing you in a second here. So you want to look at those compliance, those prescriptive requirements, or what used to be called prescriptive requirements, are now in specific sections of the code, like the specific insulation section of the code that we'll be talking in the next section here. And then performance approach allows us to use the trade-offs to meet specific prescriptive or R value requirements there. It does not override the requirement, again, for how you install something, but it allows you to have flexibility in how much R value or U value you put in a specific assembly. You can trade off almost all energy efficiency requirements, and depending on the compliance pathway that you're using, you have the ability to trade off air tightness for R values. In some approaches, you can only trade off R value for R value, but other approaches gives you more flexibility there. So what is a trade-off actually? So let's think about trade-offs. What a trade-off allows you to do is to put something more in one assembly so that you can put something less in another assembly, while at the same time keeping a balanced energy budget and balanced energy equation that is compliant with the energy code here. So if we look at this scale, this depiction of a scale here, and we say that the blue ball represents R38 insulation. If you've looked at the 2021 IECC, you'll notice that attic insulation is now at R60. And I, as a builder, might say, there's no way I'm going to put R60 in my attic. I've never done it. It doesn't make sense to me why I need to do that. I'm going to stick with R38 in my attic. And as a code official, you say that's fine. You know, you don't have to follow the R value table. You just can't use the R value table compliance option there. You have to move to a computer modeling option that will allow you to put R38 in your attic, and you're going to trade off less insulation in my attic for more somewhere else. That might be better windows, that might be better house tightness, that might be better insulation at my foundation. Whatever that is that you can trade off to say, I'm going to put more in one location so I can put less in another location, you're fine at doing that. But it gives you, and it potentially gives you more flexibility, the trade-offs, but you have to pick the right compliance pathway in order to achieve that trade-off and make that trade-off work in the context of the code requirements that are there. So that's why we have these different compliance options here, is to provide flexibility for builders, because the intent of the code is not to make it more difficult to build. It's to make it to still give you all the options that you want to be able to build with, the materials and whatnot that you want to build with, but to build within kind of the context of a more sustainable structure that's efficient, that's durable, that's comfortable, that lasts over time there. So we have these different compliance pathways through the code. Two of them are talked about as prescriptive compliance pathways. Prescriptive meaning that you have less choice, less flexibility. They're kind of the thou shalt do pathways. And then you have performance approaches there. And regardless of the compliance option, you have these additional energy features that you have to address as well. And then in the 2021 IECC, they added a tropical climate zone compliance pathway, which obviously we aren't going to talk about today as well. So again, the prescriptive requirements have things that might be about a specific installation of an attic eave baffle or a crawl space vapor retarder, or it might be about how you install attic insulation and floor insulation. So last kind of word here is that when you're looking at installations, it's going to be talking about R values, but it's also going to be talking about installation. And we want to divide those two things up so that we can understand the true installation requirement, regardless of how we might trade off R values and U values in the building envelope there. Okay, so let's get to the additional energy features first here. So depending on your compliance option, you have to choose which additional energy efficiency option you're going to utilize here. So if you're using the prescriptive compliance approach, you have to choose one of the efficiency packages that are listed in this section R408.2. If you're doing the total building performance compliance approach, you have a choice of either choosing one of the efficiency packages, but you can't use that efficiency package in the energy model to give you credit to do a trade-off, for example. Or you have the choice of basically making your house 5% better than it would normally need to be to meet the requirements of the code. And then if you're doing the energy rating index compliance approach, you only have the choice of making your home 5% better than it normally would be to meet the intent of the code. And so as we go through each of the pathways, I'll show you how this works. But before we get there, let's look at these, a quick glance at the additional efficiency packages that you can choose from. So you can choose from enhanced envelope performance, more efficient HVAC equipment, more efficient water heating, more efficient HVAC delivery systems, and or improved air sealing and ventilation systems installed in your house. Now, you might be already installing, a super high efficient HVAC system there. And if you are already installing that, you'll get credit for that. You've already met the additional efficiency package option choice there. But if you haven't done any of these things, you're going to have to choose and do something a little bit more than you normally would have there. Okay, so let's talk about the building thermal envelope again. Real quick, just because in what used to be called the prescriptive path of the code said that you also had to incorporate a vapor management or vapor retarder into the assemblies of the code. So we can't forget that there's that requirement there. That actually takes us to the IRC, and we'll take a little detour here in a second and look at that. We have to remember that the prescriptive options for the code are the least flexible in the IECC. They're basically a thou shalt do type of approach. There's no compliance tool for the base prescriptive compliance options there. You basically are just declaring to the code official, I'm going to use these R values, and these R values are listed in the R value table, and that's how I'm going to proceed in building my houses. This is really for that builder that I often hear from that says to me, just tell me what to do. And if they want that approach, it's there. It's not the best approach for building your house, but it is there. It is available for folks. So when you talk about the true prescriptive approaches, you have 4 options here. You have an assembly U-value approach. You have an assembly R-value approach. You have a cavity R-value approach. And then you have the area-weighted U-value trade-off approach here. Now, the reality is that the 2 in the blue on the right here are the true approaches that are actually used. The assembly R-value and the assembly U-value approaches really are needed because we want to do software modeling, not because somebody's going to hand calculate what the U-value is of the assembly from air film on the outside through the assembly to air film on the inside there. That is done in the context of an energy modeling software. So in order to do energy modeling compliance approaches, we need those assembly U-values listed in the tables there. So when somebody says, just tell me what to do, you're going to go to the R value table and you're going to use the cavity R value approach, because as a builder, you would be telling me as a consultant, tell me what R value I need in my cavities for my walls, for my foundation, for my rim joists, for my attics and ceilings, and that's all listed out in the R value table. And then if you want to start getting more flexible approaches here, you would start using the area-weighted U-value trade-off approach. Some people call that the res check approach, but res check really is a software. It's not a compliance option there. And there are a variety of softwares that can do this approach here. So we need to understand a little bit about R values and U values. So R values describe a material's ability to resist the flow of energy. Now, energy is always moving through our assemblies from higher concentrations to lower concentrations, in the same way that moisture moves from higher concentrations to lower concentrations. We have normative R value, which is the R value of the insulation within the cavity, and we have an assembly R value, which is the weighted R value of all the layers of materials that are inside the assemblies, again, that we need for the computer modeling approaches there. And what we need to really understand about that is that the normative R value, when I say that I'm building an R20 wall or an R30 wall, the reality is that I'm not building anywhere near an R30 wall, because the assembly R value is taking into account the percentage of the cavity insulation that's R20 versus the percentage of wood in the wall that's about R5.5 if we're doing a 2x6 wall. And when you do that calculation, you realize that the whole assembly is cut in half from about R20 to around an R10 there. And then when you add windows to the equation, which are the total weakest link in our whole assembly, we half that about again. So when I'm really proud about building an R20 wall, the reality is that my wall is probably around 5 to 8, maybe 10. And that's one of the reasons we see here that the 2021 is even more kind of aggressively trying to move insulation from our cavities to the exterior of our buildings so that we can reduce thermal bridging, we can increase the assembly R values of our assemblies out there. And so you'll see compliance approaches that are trying to incentivize or get us to do that from a sound building science kind of perspective. Now, U factors are a little bit different. So if you take the reciprocal of the R value, you get a U factor there. And the lower the U value number, the more efficient it is there. So U factors are applied to assembly. So that's why we always talk about windows with regards to a U factor, because it's an assembly of components that are coming together that are making up our window. We have our window, our glass, we have the gases or the low E coatings, we have the frames and edge spacers, all these different things that are part of the assembly. And then we have construction of components that are described by the R value there. Real quick, do I need to answer a question for the interpreter? As I see a hand raised. So just let me know if I do, because I see a hand raised.
Robbie, I'm
this-
going to pause really quick and just see if Jessica needs anything. Let's see, but she might not. We might not be able to hear her on the English channel. I'll send her an email. Keep going. Sorry about that.
Okay. What this slide is trying to do is just demonstrate the equivalency between the U factor table and the R value table. In essence, they're describing the same things from an assembly perspective in the U factor table and a cavity perspective in the R value table. But the R value table, if you just did the reciprocal of the U value that's listed here for wall assemblies at 0.045, you would get an R22.22. And you might scratch your head because the R value table says I have to put R20 cavity insulation plus R5 exterior continuous insulation on the outside of the house there. And so I have R25 in the cavity insulation. And so what we see is that because we're talking about the assembly of things versus the cavity of things, when you equal those two things out, you're actually describing the exact same thing with the same performance R value or U value there. So I hope this isn't that confusing, but I just wanted to demonstrate that the U value table and the R value table are actually describing the exact same thing there. The same requirements are listed in both those equations there. Insulation in and of itself doesn't work. The material is almost irrelevant because the material is used to trap a pocket of air. So in this illustration, we have a person who's putting on a fleece jacket. And it really doesn't matter if they're using a fleece jacket or a wool sweater or a cotton sweatshirt. The objective of the material is to trap a pocket of air. And it's the pocket of air that creates the resistance to the flow of energy from the body to the outside ambient air there. So the better that the insulation is at trapping pockets of air, it increases its R value. But if she or this person walks out to outside and it's windy outside, air is going to be moving through that insulation there. And you're not going to have a stagnant pocket of air and you're going to get cold and whatnot. And the same thing's true with a house. So we need to align an air barrier with the thermal barrier. So in our example here, they put a nylon shell over the insulated material there to get an air barrier there. And in essence, they've got an interior air barrier, which would be their skin. They've got a thermal layer, which would be the fleece, and they've got an exterior air barrier, which would be the nylon shell. And it works exactly the same with our houses. We have an interior air barrier, which is our drywall. We have cavity insulation, and then we have an exterior air barrier, which would be our sheathing, for example. And that assembly of things creates our thermal envelope that works the flow of energy. And then we decide what type of insulation we're going to put in there. And the higher the R value, usually the denser the material or the better the material is at trapping a pocket of air, whether it's foam or fiberglass. The objective is to get a stagnant pocket of air that resists the flow of energy from higher concentrations to lower concentrations. So that's what we're looking for here. So the R value table tells us how much insulation is required, but again, it's only looking at the cavity or component R value there. And so you'll see that if you bought an early version of the code, that there were some mistakes in the printing of the code. So make sure you get the errata that's put out there that tells us all the things that were missed in the first printings of the code. So everything in red here was missed in the first printing of the code. And that's pretty dramatic here, because you can see in our climate zones, the whole wall R values were not printed correctly there. But the other thing we see here is that we have a lot of choice. So we have a lot of flexibility within the confines of a prescriptive approach here. That is usually the most limiting part of the compliance approaches that we have here. You can choose to have an R30 wall. You can choose to have a 20+5. You can even use a 2x4 wall if you put R10 continuous on the outside, and or you can put all of your insulation to the outside at an R20 there. The other thing that changed was the R60 in our ceilings. But that really, I think, is about the gist of the changes in the R value table. You can see that it didn't change that much there. The R60, the wood framed walls are the big things. This chart just kind of gives you an idea of how things have changed over time. We're not going to spend a lot of time there, but you can see that from the 2009 to the 2012, it really hasn't changed until the 2021 when we look at wall assemblies in climate zone 6, for example, there. So some things have changed over time, but some things really haven't changed over time. The other thing we want to do is make sure that you look at the footnotes underneath the R value table, because there are some installation requirements, but there are also some clues about how the table is structured and whatnot. The first footnote is about the R values are minimums. And in essence, it's talking about when insulation is not installed properly, it loses R values. So it's talking about compression, especially of fiberglass bats. As you compress a fiberglass bat, it loses its R values. So in essence, it's saying that we need to install the insulation and install it well there. A lot of the footnotes here are talking about what CI means, so continuous insulation versus cavity insulation in our assemblies there. Footnote D gets into the slab insulation. What's represented on the R value table for slabs is the slab edge insulation. So if you are building a heated slab, you also have to put insulation underneath the slab. So you're basically building a tray, an insulated tray that you're putting the concrete in to separate the conditioned space from the unconditioned space, and also ensure that the heat in that slab is getting reflected or pushed into the home itself. And then there's another description of cavity versus continuous insulation for a different component of the assembly here. Now, I guess I should point it out. I don't like to point it out, but footnote I here that I don't have highlighted does allow one to put in a lower quality window at elevation here. And the rationale there is that when you start getting low U value windows, you have to start adding some type of gas to the assembly there, like an argon or krypton gas. And if those windows are made at lower elevations, when it comes to elevation, it's unclear whether that gas is still in the window unit as it was when it was constructed there. So they give you an allowance to put in a little bit less U-value window there. But the reality is that in order to pass the compliance options there, it's going to be difficult to not have a good window, and also to begin to think about the window to wall ratio. How much glass we're actually putting in our houses is making it more difficult to comply with the codes there. So it is something that architects and engineers really need to be thinking about there. Okay, so taking a little bit step back to that vapor retarder section here. So we know the insulation that we need to install, but we have these houses that are 100-year-old houses that are drafty, uncomfortable, yet they're 100-year-old houses. And so the big question is why this house lasts over time. Why is it durable? And the biggest reason it's durable is because it has incredible drying potential there. And when we take this kind of notion of drying potential and we look at how new houses have built, our living expectations of how we live in our houses have changed so dramatically over the course of 100 years that the way that we build our houses also have changed, and we've changed the drying dynamics of our houses. Just by adding insulation to our houses, we are changing the drying dynamics of our houses. Therefore, we also need to think about how we're going to incorporate the vapor retarder requirements of the code. We've changed the way we build, so we need to understand moisture flow in relationship to thermal flow in our houses there. So as we add higher R values in our modern insulated buildings and assemblies, we do increase efficiency in our houses, but we reduce the exterior sheathing temperature because less of the energy is flowing through that assembly, or it's flowing through at a much slower rate there. So the code understands that, and it understands the building science around that, and that cold surface can create condensation issues there. So this is, again, one of the reasons why in the R value table, you'll see the kind of this emphasis on considering moving insulation to the exterior. Yes, I could change compliance approaches and potentially trade off that continuous insulation on the outside, but does it make sense for me to do that from a durability, efficiency, resiliency kind of perspective in our houses? Because we're going to have a certain amount of R value there. And if I allow a lot of heat flow through and I keep the exterior surface warmer, yeah, it might be better, but at what cost? A comfort cost. Again, our expectations of our houses are to be able to walk around from room to room and floor to floor in basically our underwear. Am I going to be able to do that if I don't build an assembly that actually works and performs to be able to do that? So when we're talking about vapor and vapor movement, we have to understand that this diagram on the lower left here is describing the pathways that moisture can take. Moisture can flow by the process of diffusion, which is described on the right side of this slide in that diagram. Moisture moving from higher concentrations to lower concentrations directly through the pores of the material. Generally in Colorado and the Gunnison Valley there, it's going to be moving from the interior of the building where we have higher moisture contents through our building assembly, so actually through the pores of drywall into our cavities and ultimately to the outside where it's drier outside. And then it also can move with air. And the diagram on the left side here demonstrates pretty dramatically that over the course of a heating season, that a significantly more moisture moves with air than ever has the ability to diffuse through a sheet of drywall there. So the vapor retarders have been requirements of codes for quite some time, but they are focused on trying to stop diffusion or moisture moving into our assemblies by the process of diffusion. And now we realize that air leakage is really the more important issue there. And that's, if anybody follows Passive House, that's why Passive House construction is looking at building the houses so tight because they don't want that moisture getting in these assemblies and these thicker wall assemblies that have really cold exterior sheathing there. So when you look at the IRC and the vapor retarder requirements, you see you have a class 1, 2, or 3 option there. We really never want to put in a class 1 vapor retarder, which would be an example of poly vapor retarder that has a perm rating of 0.1 or less. Craft paper, class 2 vapor retarder is better. It gives us more drying potential. It has a perm rating of 0.1 to 1. But ideally, we just would rely on latex paint that has a perm rating between 1 and 10, or some type of class 3 vapor retarder there. So then we have sound drying potential. And you always have to build your assemblies understanding the weakest link in the assembly, which would be the most vapor impermeable piece of the assembly. And we want to promote drying potential in the other directions, which basically means don't put a class 1 vapor retarder on both sides of the assemblies there. Now the code is saying, well, if you have to put in a class 1 vapor retarder, well, the code doesn't really say this, but if you have to put in a class 1 vapor retarder, it's recommended that you always use a smart vapor retarder. And a smart vapor retarder allows you or allows the assembly drying potential. So because there are no rules about how vapor retarders are installed, there are no manufactured instructions for how to install a vapor retarder. There's no guidance in the code for how to install it. And we tend to install them really badly. And therefore, moisture bypasses the vapor retarder with air, and it ends up trapping the moisture in if you have a traditional class 1 vapor retarder. So the smart vapor retarder allows any moisture that does get bypass it with air to dry back out in one direction. It stops it in one direction from the process of diffusion, but it allows it to dry in the other direction by the process of diffusion. And so some of the examples of that type of smart vapor retarder air control layer are Intello or Myrex, or Certainteed has one called Membrane that works as well there. So if you have to put in a class 1 vapor retarder, make sure that you're in and you install it well, and you can see all the joints are taped and whatnot. It can also be an air control layer in your home. But if ideally you would use something that's more forgiving, like a class 2 vapor retarder, and you can see in climate zones 5, 6, 7, and 8 that if you do that, you have to have some exterior continuous insulation, R value, on the outside of your house there, so that you're ensuring that if moisture ever were to get in that assembly, that it has less of the potential to condense, because you're warming that first condensing surface, that exterior sheathing there. And you can see if you use a class 3 vapor retarder, you now have a choice of either doing a vented cladding or continuous insulation. And you can see that the R value, if you take the R value here in climate zone 6, for example, the R value table would say to put R5 on the exterior. Well, this is telling us to put R7.5 on the exterior. So what the code has done is it's adopted the sound building science and understands the ratios of the total assembly R value and how much you need exterior continuously to warm that surface there to make it work and work well there. Ideally, we actually would be marrying a vented cladding and a continuous insulated cladding to give us the most robust and enduring, durable assembly that we can build out there. But I wanted to show you this because it's going to change your dynamic in terms of the type of insulation that you're going to put on continuously and the requirements for the R value there, especially in the climate zones in the Gunnison Valley up there. Okay, so all of these other compliance approaches beside the R value table require some level of use of an energy model. And energy models are great tools that we need to do. They're simplified ones and they're more robust ones out there, but they're definitely worthwhile to take into account. Now, regardless of the compliance approach that you use, again, you still have to do the energy efficiency addition there. The other thing that you have to provide is a certificate. This is a certificate, a compliance document that you need to comply with and post in the house after the construction of the house is done. And the reason I put it here is that these software tools can print out this certificate. So the certificate in the middle here is a printed one. For the R value compliance approach, this is a hand-generated certificate that I've created that I'll turn in when I'm working with a builder that's using a prescriptive compliance approach there. The idea of this certificate is that it benchmarks the energy features of that house so that the owners have a record of what's behind the walls there, so that when they do an addition or alteration to the house, they understand the starting point of that house. So it's kind of an important certificate that we're going to do here. Now, energy modeling is great because it allows us to, what I say, fail quickly and succeed even quicker because it gives us the ability to do scenario modeling. So I can throw a lot of different things at the energy model and see how it's going to change its performance. And even more so than that, I can figure out what's the most cost-effective way to achieve my goal. Now, my goal might be just to be compliant with the code, but my goal might also be to maintain better comfort in the house, to maintain better durability, better resiliency in that house. And depending on the type of energy model that you're doing, it can help you make those decisions. And you can fail before you've ever spent any money on the project to buy materials and whatnot. And so therefore, in my estimation, you can succeed a lot quicker there. So all energy models basically work the same way. They're describing the delta T across the assembly. And delta T is just a fancy word for the temperature difference across the building thermal envelope, that boundary that's separating conditioned space from unconditioned space. So the picture in the upper right-hand corner demonstrates that it's 70 degrees inside, 10 degrees outside. The delta T, the temperature difference, is 60. So I know for a fact that the energy is moving from inside the building to outside the building. So we're in kind of this wintertime condition there. So the softwares are describing all the components of the building in relationship to their delta T. And the delta T begins to get described by the code. So the code tells us that the interior design conditions, when we're sizing our HVAC systems for the house, we have to use 72 degrees for our heating design temperature inside the house and a minimum of 75 degrees for the cooling design temperature inside the house. And then the jurisdiction is going to jump over to an ASHRAE standard to be able to tell us if what the exterior design temperatures are on the worst and coldest days of the year. I didn't take the time to look at it in the Gunnison Valley, but I think it's below zero, somewhere around -10 or 20 in the exterior wintertime design conditions. And I'm not exactly sure what the summer design conditions are, but it is climate specific. So Denver, for example, is at 3 degrees and 93 degrees. So you'll have a summer design condition, kind of worst case design condition, and a wintertime worst case design condition specific for your climate there. Now, what the software is also doing is creating what we call a reference home. So a reference home can be described and has a specific definition that says it's a standard set of specifications that generate a specific, consistent, and quantifiable energy performance for that house. So what the software does is we do a takeoff of the house and we rebuild that house inside the software. And the software is sophisticated enough that it builds a duplicate. So it builds two houses inside the software that are geometric twins of each other. The first house is called the reference home, and the first house is overlaid with a standard set of specifications that generate a specific, consistent, and quantifiable energy performance. So you think about the R value table. The R value table, if I implement the R value table, I have a consistent, specific, quantifiable energy performance that's happening as a result of implementing that. So instead of using the R value table, the software uses the U value tables, which are the exact same things, but describing them as an assembly of things rather than a cavity. It's R value there. So the reference home is overlaid with the assembly U values from the code. The rated home or the builder home, which is a geometric twin of the reference home, is overlaid with whatever the builder desires to install for the assembly energy components and specifications for that house. Then the rated home is compared to the reference home, and if the rated home's performance is equal to or better than the performance of the reference home, it is compliant with the code. And there turns out to be three ways that you can demonstrate that compliance. The first way is using area-weighted U values. So in this kind of simplified approach here, we have two houses that are geometric twins with each other that we're comparing to each other. The first house is called the reference home, and we're using the assembly U values that are in table R402.1.4 overlaid on that house. And the builder's house, we're overlaying U values for the assemblies that the builder desires to do. So for example, the reference home might have a assembly U value for its attic that equals up to an R 60 in that attic. And the builder again might say, no, I want to put R 38 in my attic. And that's perfectly fine if the end result shows that the builder's house is the same or lower with regards to area weighted U value. It will meet the intent of the code there. Okay. So the total UA alternative is this method of what we call performing conductive energy trade-offs. So we're only able to trade off R values and U values in the building thermal envelope there. Now, where we gain flexibilities are moving to other performance approaches there, other energy modeling approaches that enable me to trade off maybe house tightness for R value and whatnot. This approach is a simplistic energy model, but it can be pretty powerful. So, and it gives you that ability to fail quickly and succeed faster that we were talking about. So I believe that every builder should at least be using a free software like ResCheck and doing a simplistic energy model to be able to determine the best, most cost-effective way to build their house in order to meet the intent of code. Because you get these mathematical trade-offs of R values and U values that equal each other. The other thing that the software does is it takes into account the entirety of the assembly. When the biggest part of that assembly, from an energy perspective, is the thermal bridging that's happening in the framing materials out there. We build our houses with a lot of wood, and we add a lot of extra wood when we don't need to. We over-engineer our houses to a large extent as well. And all of these things are thermal bridges that reduce the overall wall R value here. So this is an example of that. Just quickly here, we have a 2x6 wall on the left and a 2x6 wall on the right, but on the left it's 16 inches on center framing. On the on the left it's 16 inches on center framing. On the right it's 24 inches on center framing. But the assemblies are the same there, and you can see that the total assembly R value is very different. The cavity R value is 21. We have R3 windows in it, and my total wall R value, assembly R value, is only 8, almost 9 in the 2x6 16 inches on center, whereas it's almost 10 in the 2x6 24 inch on center framing there. So it's pretty dramatic there. Now, if I add continuous insulation here, on the left, we've added R6 continuous insulation. On the right, we've added R9 continuous insulation. We've increased the overall assembly R value of these assemblies quite a bit, from about 9 to 11 on the left side, from about 10 to 12 or so on the right side of the assembly there. And so again, that notion that we're building really highly super insulated walls might or might not be true, depending on how we put the assembly together and we reduce the thermal bridging components and whatnot. Here's the last example. And in this example, we've increased the efficiency of the windows here. And now we're getting into some wall assemblies that actually have some meaningful R value or resistance to the flow of energy. On the left side, we went to an R5 window with that R6 continuous insulation. And you can see the window to wall ratio is at 15% here. So I know we love our views in the Gunnison Valley, but when we get up into the 20 and 30% window to wall ratio, we're just really making it difficult to comply with the codes, or you probably aren't going to be able to, to be quite frank. It's very difficult to do any type of trade-off when you've got really high window to wall ratios there. Okay, last thing I want to talk about with this pathway is that there are a number of different softwares available that can be used to do the total area weighted U value compliance approach here. ResCheck software is a software, not a compliance approach. It's a free software, so anybody can download it or use the online version. You just want to make sure that you're using the right version or selecting the right code for your particular jurisdictions that you're dealing with. RemRate and Ecotrope are energy rating softwares, so you have to be an energy rater to be able to gain access to these softwares, but they can do all the compliance approaches as well as generate an energy rating index score and demonstrate compliance for programs like Energy Star or the DOE Zero Energy Ready Home program as well. And you have now the ability to take advantage of the scholarship programs and start potentially doing some career development if you want to, and learn how to use those softwares there. So this is an example of a compliance certificate for the total UA compliance approach. This is the ResCheck software here. The first thing you need to determine is that you're using the correct code. So you can see in this example that this is for the 2012 IECC, not the 2021 IECC. So that could be, if you're a little bit dyslexic like myself, I might not catch that in my plan review. So you want to make sure that you're starting out correctly here. Then you want to look at, is this house compliant or not? So I'm just going to blow that up a little bit. You can see that this house is 3.2% better than code, which basically means that the area weighted U value for the reference home is 375. The area weighted U value for the builder's house is 363. That's a lower number than the reference home. Therefore, it meets the intent of code. It passes code there. So you'll need to turn in this compliance document if you're using this compliance approach in order to get your building permit, in order to be reviewed so that the builder understands what you're proposing. I'm sorry, the code official understands what you're proposing to build out there. Here's an example of the same reports, but generated from the Ecotrope software. Again, at the top, it needs to say it's projected versus confirmed up there. So the code official knows that the house hasn't been built already, that you're turning this in to get your building permit there. It will show the results for the reference home. It will show the results for the as design or builder home there. And then it will show the overall result here. Is it passing or failing there? So again, make sure you're doing it for the right code edition. There you can see the Ecotrope report is for the 2021 IECC, but the RemRate report is for the 2018 IECC. Here, The other thing that you need to turn in is an energy code inspection checklist. This gives the code official a little bit more information about how the assemblies are being constructed, and helps potentially guide them through the inspection process. Some jurisdictions use it, some don't use it, but the code basically requires that you turn in that certificate there. So it'll give the property, it'll give some general information about the house. The other thing that often happens at plan review is there's a quick calculation maybe of the square footage and volume of the house to ensure that the takeoffs were done within reason. Everybody's going to have a little bit different takeoff there, but you want to make sure that you've got, if this house is 65,000 square feet, you want to make sure that you're not actually looking at a house that is 10,000 square feet or something like that. You haven't made a big mistake there. I'm just going to skip that. Okay, so that kind of describes the area weighted U value compliance approach, and we're going to move into the total building performance compliance pathway here to get this house through code. So this compliance pathway utilizes a little bit more robust energy model. But it also is within the confines of the code here. So the code is looking at only heating, cooling, and surface water energy use only, which means that we're not talking about the efficiency of the mechanical systems themselves, and therefore I'm not able to trade off an 80% or 90% AFUE furnace for less R value in the assembly. What we're talking about are the heating and cooling and water heating loads of that house there. And that's what it's looking at. So the code really right now doesn't mandate any specific efficiency of our mechanical systems at all. It's really concentrating on the building thermal envelope. And that's why the additional efficiency packages are put in place in order to give you some credit for an incentivization to do higher efficiency equipment in the home itself there. So again, you have to address the additional efficiency packages there. So you have a choice of choosing one of those efficiency packages, like a higher efficiency HVAC system, or you can demonstrate that the cost compliance report is showing that the house is 5% better than the reference home there, which is pretty easy to do. You also have to comply with all of these requirements. So these requirements come from the specific insulation requirements, mechanical requirements, lighting requirements. All of the things that are listed in this table are required in essence for any and all of the compliance approaches that you're using. They just put everything in this table to make it easier because they remove the kind of the terminology of mandatory and prescriptive requirements there. And then we have the performance-based compliance. Because it gives you the ability to trade off things, the code has introduced this concept of a backstop, which limits the amount of trade-off that you can do. And for the building performance approach here, the simulated building performance approach, it says that the building thermal envelope shall be greater than or equal to the levels of efficiency and solar heat gain that's described in the 2009 International Energy Conservation Code. So if we went back to the R value table in the 2009 International Energy Conservation Code, you would see that the requirement there for a 2x6 wall is R20. So basically what this is saying is that I cannot trade off my wall assembly to less than an R20 there, where you could do that energy modeling and demonstrate that it meets the code, but the backstop is saying you cannot install anything less than R20 in the wall assembly there. Again, it's trying to protect the integrity and soundness and performance of the building thermal envelope there. This type of modeling is a more holistic modeling there. So it's kind of this building science approach where you're looking at the performance and integration and synergy of all the different pieces of the assembly there, and therefore it can potentially create trade-offs that have certain pieces of the assembly that aren't performing well at all, versus and trading off to get really good performance maybe in my attic and less performance in my walls. And so that's why, again, these performance backstops are put in place there to protect the entirety of the building thermal envelope there. So just like the total UA approach, the building or simulated building performance approach is a twin house concept here. So we have the reference home that is built off of a specific table that's in the R405 section of the code. Sorry, I should say 2021 reference designed house versus the builder house there, which is a geometric twin of the reference home there. It's overlaid with whatever the builder wants to do within reason, within the confines of the 2009 IECC. And if the builder's house is better than or equal to the reference home from a performance perspective, it will meet the compliance of the code. Now, the question here is that it's not using area weighted U value as the metric to demonstrate compliance. It's using annual energy cost to demonstrate compliance with the code. And it's also giving us the ability to do not only conductive trade-offs like the UA trade-off approach is allowing us to do, but it's allowing us to do convective trade-offs and radiant energy trade-offs. So it's taking into account all the different ways that energy moves through our buildings there. And so if I build a tighter house or I bring my ducts inside the building envelope so they're not radiating energy out to the ambient outdoors or to my ventilated attic space, I'm potentially able to trade off that efficiency construction for less R value somewhere else. I'm not just limited to an R value to R value or U value to U value approach here. I can now trade off other things like air tightness for R value there, which is important to understand because it gives us greater flexibility, more ability to figure out cost effectiveness of how we're going to put our assemblies together to make them work and work well here. Now, the compliance reports, we have to turn in a proposed design to get our building permit, and that would be a proposed cost compliance report. And upon completion of the house, we have to submit a confirmed compliance certificate in order to get our certificate of occupancy from the house there. So this is what that certificate looks like. You can see up in the upper corner there, it's saying results are based off of projected analysis here. And that analysis is for achieving our building permit here. We have the energy costs of the reference home. We have the energy costs of the designed home. The designed home is less than the reference home, therefore it meets the intent of the code. And in this case, it's 16% better than. So I've demonstrated my additional efficiency requirement as well here. I had to be at least 5% better than the reference home. And in this case, I'm cruising past that at 16%. So we're doing well here. We're meeting the intent of the code. That needs to be signed by the person who's done the software analysis and turned in to get my building permit. And then this one you see up in the upper right corner, it says confirmed there. This is the type of report that you would turn in to get your certificate of occupancy. So the compliance report there. Now you have to also turn in an inspection checklist, but you also have to comply with 3B here in this section that says that it shall show the results for both the standard reference design and the proposed design. So this is the energy code inspection checklist that looks very similar to the area weighted U value compliance approach checklist, but it's not fulfilling the requirement of 3B here. 3B is actually looking for the proposed home design summary report for the reference home and for the proposed house there. And basically this report is demonstrating the software inputs and description of the assemblies for each of these assemblies. So from foundation through the framed walls, it basically outlines all of the components and entries into that software for this approach there. And so the jurisdiction has the ability to ask for this report. Often you just turn it in, right at the beginning there. The last thing I wanted to talk about with this compliance approach, because you can't use a ResCheck software. You have to use that REMRate or Ecotrope or that energy rating type software there. As a byproduct of this approach, you might be getting a HERS energy rating index score. So you have to be clear that that HERS energy rating index score is not used for compliance with this approach. Your jurisdiction might be requiring a HERS energy rating index score. So if that's the case, you would be turning in the energy rating index score and not the cost compliance report. But in what I'm describing here, in utilizing this compliance approach, it's only the cost compliance report that you would be turning in to get your certificate of occupancy and your building permit. And often if you turn in the energy rating index, it tends to confuse the plans examiner or the code official, because they don't know what compliance approach am I trying to use here. So utilize the HERS energy rating index as education for the builder, for the architect, for the homeowners that are building that house, but don't turn it in for compliance if you're using this compliance option there. Okay, so next and lastly, we're going to talk about the energy rating index alternative here and this compliance pathway. The energy rating index was developed by ResNet. They created this system here. You can think of it like a golf score. The lower the energy rating index number, the more efficient the house is. You can also think of it as a miles per gallon type of rating for homes. So with miles per gallons, I don't care if it's a huge Dodge or whoever makes the Hummer type car, or some big truck, or a small like Hyundai or Toyota type car. When I look at the miles per gallon rating system, it gives me an indication of the efficiency of that car from a miles per gallon perspective. In the same way, it doesn't matter who the builder was, who manufactured the home, what the size of the home is. And when I look at the HERS energy rating index score, it gives me an idea of the efficiency of that house there. So it's a good tool to definitely use. It helps us evaluate the energy efficiency assets of the house. So when you're doing a true HERS energy rating index score, I don't care how the insulation was installed. I don't care about any of the features in terms of how they were installed or how they're performing. My job is to evaluate the energy assets and reflect them properly in my software analysis to generate an accurate energy rating index score for that house. When this starts being used for code compliance, I have to mentally change my perspective of how I'm approaching the house, because I do care about how the insulation was installed. And is it been installed in accordance to the requirements of the code? And then I have to think about afterwards, after it's been installed properly, I have to think about how I am going to accurately reflect that specific assembly in the energy rating index there. Now, the HERS reference home is benchmarked at 100 on the scale, which is equal to the 2006 IECC. Every point in relationship to 100 on the scale is equivalent to 1% of energy use in the house. 0 on the scale is equivalent to a net zero energy home. It's net because the energy rating index doesn't care if you use all electric homes or if you're using gas or not. Over the course of the year, if you're 0 on the scale, it's going to net out that energy use, which means that you have to have some type of renewable on the house, some type of PV system, most likely, on that house. And it also means that the lowest possible score without renewables on the house is somewhere in the 30 to 35 index range there. You can't get below that without adding renewables to the equation there. So that's another kind of important thing to know. And then lastly, the Department of Energy says that the average existing home out there is scoring around 130 on this system. And I'd say the worst house that I've ever seen or worked with was about 250 on the scale, which is pretty bad, obviously. And the best house was about -20 to 25 on the scale there, meaning that it had a huge renewable system on the house, and it was oversized. Basically, it was producing way more energy than it needed there. Now, again, the HERS Energy Rating Index score is not what is used to demonstrate compliance with the IECC. Some jurisdictions have amended their code to utilize the ResNet HERS Energy Rating Index. And so you need to know which jurisdictions are utilizing that and which jurisdictions are not utilizing that. And we'll cover that here at the very end here. The HERS ERI and the term ERI itself has really become kind of the Kleenex, Coke, Xerox of the industry. Energy Rating Index just describes the index score. The term HERS, or Home Energy Rating System, is a proprietary term from ResNet, and proprietary terms like that can't get adopted into the language of the code. Therefore, they developed Energy Rating Index score. It does mean that we have to be kind of particular with our language. You know, just like I want to talk about drying versus houses breathing, I want to talk about the HERS Energy Rating Index score versus the IECC, or the code's Energy Rating Index score, because it turns out that they are different from each other. And I'll show you why that. When we're using this compliance option, again, we have these requirements that we have to abide by and implement when we're installing certain things like attic eave baffles or vapor retarders or mechanical systems or lighting there. So we want to go to this table and make sure that all of these requirements are taken care of when we're installing certain things in our houses. We have to deal with the additional energy efficiency requirement as well. So the compliance with this is saying that I have to achieve in climate zone 6 an energy rating index score of 54. Now I have to achieve that. That's basically my target, and I have to design an assembly that will be equal to that or perform better than that, so lower on the scale. When the additional efficiency option is taken into account, we have to take 5% of that and reduce it by 5%. And I said earlier that we benchmark the energy rating index score at 100, and every point in relationship to 100 is 1% of energy use. But every point in relationship to 54 is not equal to 1% of energy use there. So I'm doing the math and taking the percentage there. So in climate zone 6, for example, instead of having to achieve an energy rating index of 54, I have to achieve an energy rating index of 51 there. So that's really my starting point. Is not what's represented in this table. It's 5% lower than that, because that's taking into account the additional energy efficiency requirement that's laid out in sections R408 of the Energy Code there. Okay, so we know where our starting point is now. Then we have to decide, are we going to put renewables on this house or not? Because the backstops that are associated with this compliance approach are dependent on if we're using renewables or not. And remember, the backstops are trying to protect the building thermal envelope. And when I'm doing an energy rating model, it's the most sophisticated energy model that we're doing in relationship to code. There are even more sophisticated energy models out there, but from a code perspective, it's the most sophisticated energy model, and it's taking into account mechanical efficiencies. It's taking into account renewable efficiencies, as well as R values and U values and house tightness and duct location and all those different things. So it's basically taking into account every single energy component of the building, whereas the other energy modeling approaches are not doing that. So if I'm using if on-site renewable is not included in the energy model, then the building's thermal envelope has to have a total UA that is less than or equal to 115% of the 2021 IECC. So if I figure out what the UA of 2021, so for example, the 0.045 that's showing up there for framed walls, I would have to multiply that by 1.15 and I would get a bigger number. So it's in essence, it's telling me that I can do some trade-offs, but I can only trade off to a certain limit there. Because remember, the higher the U value number, the less performance it is. The lower the number, the higher, the greater the resistance to the flow of energy there. So it is allowing some trade-offs, but it's giving me a backstop. It's saying I can't trade off over a certain number there based off of the 2021 and 15% of that number there. If I have renewables on the house, then the building thermal envelope shall be greater than or equal to the levels of efficiencies that are described in the 2018 IECC. So here's the 2018 IECC. So if I put a renewable system on the house, I have to have in climate zone 6, R20 plus 5 building assembly or equivalent in that assembly there. So again, it's giving me a backstop. I can't trade off. I can't use renewable systems to trade off for something else in that equation there. And this is an example of why that is the case. So if I have a 2-story house that's 2,800 square feet, and it's built with the house specifications that are on the right of the slide, I'm going to achieve an HERS energy rating index of 100, which is equivalent to the 2006 IECC. Now, I can put on a pretty small, relatively small PV system, and just that addition of a 6.4 kilowatt PV system is going to drop the score from 100 to 55. So you can see how dramatic renewable energy is to the equation here. You can see also why builders were really excited about adding this compliance approach to the path there as a compliance option in the code here, because a lot of builders misunderstood what this approach was trying to do. And they didn't understand the backstops there. So you'll see some of the large national builders back in 2015, when this was adopted into the code, they went out and they bought some solar companies there because they thought that they could go back to, really poor building thermal envelope and put a lot of PV on it and meet the intent of code and potentially figure out a more cost-effective way to build the house. What they didn't take into account, which the code is taking into account, is that when you build a poor building thermal envelope, you're going to get a lot of callbacks, especially in your climate in the Gunnison Valley there. So you're creating an uncomfortable building thermal envelope and compensating for that by putting a lot of PV on it. It's just not going to work. And the code is ensuring that you're not able to do that type of thing there. Now, the reference home design in 2015, we only had the mortgage industry national standards there, the MinHERS standards that ResNet created. And therefore, in 2015, when the energy rating index approach was added to the code, it referenced the 2006 International Energy Conservation Code. And the softwares basically used the ResNet standards to develop it. In the 2018 IECC, ResNet and ICC came together and they created Standard 301, which defined how to build an energy rating index score there. And the code was linked specifically to that version of the ANSI standard. So it's a 301-2014 version of the code. In the 2021 IECC, the ANSI standard 301 was updated, and so the code used the most recent version of the update. So that means that if you're using the 2018 version of the IECC, you're linked to an older version of the ANSI 301 standard, and your energy rating index score is going to be different than if you're linked to the 2021 IECC there. So that's one reason why the HERS index and the code indexes are a little bit different here. Now, you can also see that during the different code cycles here, that the energy rating indexes have changed just because the code development community thought that they needed to be different. So in climate zone 6 in the 2015, it was 54, and then it went up to 61 in the 2018, and then it went back down to a 54. But remember, the additional efficiency requirement in the 2021 IECC makes that 54 really a 51. So your requirement is 51 in the 2021 IECC. This is an indication that the different compliance options aren't equal in terms of they all are demonstrating compliance with the code, but you would think that all the compliance options would have a common starting point. You'd have options and flexibilities to get to your building permit, and that all of them would have the same level of efficiency as an outcome. And that's not true at all. This approach, you will have a more efficient home than you would if you just use the R value table, for example, there. So, but from a modeling perspective, it's basically the same twin house concept where you have the reference home built off of the energy rating index score requirements and the standard 301 requirements and the code requirements. And then you have the builder's desired specifications with backstops and other things. And you're creating a energy rating index score, and you're trying to determine is that energy rating index score equal to or lower than that required by the table that's in R406.5, which would be after the additional energy efficiency in climate zone 6 would be a 51 that we would have to achieve there. Another thing that changed in the 2021 IECC is verification of this process. So the ERI compliance itself shall be completed by an approved third party, because generally code officials don't generate energy rating index scores. HERS raters and other, well, really only HERS raters right now are generating energy rating index scores there. But that left in question, what about all the other requirements of the code? Who's supposed to verify those things? The energy raters weren't clear if they were supposed to verify all those other components of the code or not, or just generate the energy rating index score. So this section was added to, and it says now that those other requirements in table R406.2 shall be completed by the authority having jurisdiction or an approved third party. And in the 2024 IECC, the approved third party has been changed quite a bit in Chapter 1 to try to get to this understanding of, in essence, the code official, if they're going to rely on an approved third party, they need to have a dialogue with that approved third party, and in essence, a scope of work document that demonstrates what the third party is supposed to look at and what they're not supposed to look at there, so that everybody is crystal clear how to demonstrate compliance utilizing an approved third party there. Compliance reports are required still. You have to turn in for one for the proposed design and one for the confirmed as-built home to get your certificate of occupancy. So the proposed design is to get your building permit. The confirmed compliance reports are to get your certificate of occupancy there. And then because renewables often play a bigger role in the energy rating index approach, they talk about the renewable energy credits, and it tells you how you have to address the renewable credits, but it really doesn't tell you about who decides which option you're going to use here. Are you going to retire the credits, or are you going to transfer those credits to the homeowner? Is basically your two options here. I think the idea is that anybody can decide. You just have to declare to the code official which option you're ultimately using there. So the other thing that we see is that the two energy rating index scores aren't the same. So I have the HERS energy rating index score on the left, which is a 63 for this house, and the code energy rating index score for the same house is a 78. So we've got 15 points difference here. They've done some work to take that difference, the large difference, away, so that it's a little bit smaller, but it's still, they're not going to be the same, and they never will be the same. So it's really important that the jurisdiction determine which energy rating index score they're going to use, because it's causing lots of confusion across the country right now. So why are things different? Again, the R406 section, the energy rating index section, was established in 2015. IECC has no oversight over the software providers that are used to make this analysis. Therefore, the software developers just adopted the ResNet HERS standards in 2015. And so in the 2015 version of the energy rating index, the code ERI and the house ERI were basically the same thing there. Then in 2018, we specifically start referencing the ANSI 301 standard for how to generate an energy rating index score. It happens to be the same standard that ResNet uses to develop the HERS energy rating index score. But during the adoption process there, the code amended the ANSI 301 standard there. And where they amended it was with regards to ventilation. So the HERS ERI uses the ASHRAE 62.2-2013 version of the the ASHRAE standard for whole house controlled mechanical ventilation. And the IECC Energy Rating Index uses the 2004 version for whole house controlled mechanical ventilation. And there's a huge difference in the ventilation rate. And as we talked about earlier, a lot of energy is transported by air. So when you're ventilating a house, there is an energy penalty associated with that. And but we still want that ventilation for control and predictability of airflow and moisture flow in our houses there. But that difference is the biggest difference that led to the extreme difference in both the energy rating index scores for the same houses there. But there's still more here. The ICC can only reference a specific version of the ANSI standard there. So the 2018 IECC, for example, is still linked to the 2014 version of ANSI standard 301 there, and it will never change. Whereas that ANSI standard is under continual maintenance. Every 3 years, it's getting updated. But the 2018 version of the IECC never gets updated. It just changes over to a new version, which is now the 2021 IECC. So the 2021 is linked to the ANSI 2019 version of the 301 standard there. So the ResNet HERS is tied to the code. And this is another reason why the two scores are different, because the HERS energy rating index score is a dynamic, ever-evolving system that is changing immediately as the ANSI standard is being updated and changed, whereas the code isn't being updated and changed until the new version of the code comes out there. So as an example of this, if we have a home permitted in the fall of 2020 that's seeking and to use the energy rating index compliance approach, you would think that it would be using the 301 2019 version of the standard. But if the state is only adopted, or the jurisdiction has only adopted the 2018 version of the code, they would be using a different version of the code. The result would be, again, different index scores because the code is linked to an older version of the ANSI standard there. So hopefully that's not too confusing, but it's a reality out there. What we know for you guys in the Gunnison Valley is that the city of Gunnison has adopted the 2021 IECC with no amendments, and therefore it's using the energy rating index score from the IECC. There. The Gunnison County has adopted the 2021 IECC and to use the ResNet HERS ERI score instead of the IECC Energy Rating Index. They also say that dwellings greater than 5,000 square feet have to use the Energy Rating Index compliance approach. So the ResNet HERS Energy Rating Index compliance approach. Houses that are smaller than 5,000 square feet can use these other compliance approaches that we just talked about. And then there's also some exterior snow melt and pool and spa restrictions that you should look at as well. And then Crested Butte has adopted the 2021 IECC. They also have amended the Energy Rating Index approach to utilize the ResNet HERS Energy Rating Index instead of the IECC scoring system there. Comply with the IECC using available compliance pathways. But if you choose to use the Energy Rating Index score system, you'd be using a ResNet system there. They've also added additional certification and requirements using the DOE Zero Energy Ready Home program. So you want to become proficient with that program and those requirements if you are building within the town of Crested Butte or the city of Crested Butte. Electrification, vehicle readiness, and all electrification homes. So there's was talked about at the beginning of the session here, there have been some significant changes in the Gunnison Valley. So you want to make sure you know where you're building and how you're going to comply with the codes in that particular approach there. So compliance reports, lastly here, we have the compliance reports to get your certificate of occupancy. You'll need those duct leakage reports, air leakage reports. We'll be talking about ventilation requirements a little bit in the next session next week. And then those certificates. And then if you're choosing to use the prescriptive pathway, you'll also have to provide an insulation certificate because now the insulator is basically certifying the R value at the time of install, especially for R values that don't have an R value mark on it. So you have to provide that certificate. For the total building performance approach, which is its new name in the 2021 IECC, you have to provide the projected or confirmed cost compliance report, as well as the insulation certificates and those other compliance documents listed above, like air leakage reports and whatnot. And same with the Energy Rating Index pathway, whether using ResNet or IECC ERI scores, you still have to turn in a projected and confirmed ERI report there. So to conclude, the intent statement of the code says the code is intended to provide flexibility, to permit innovative approaches and techniques to achieve that objective there, which really means that we need to understand the intricacies of the code in order to understand the flexibility of the code. And that's why I really like this statement from the Dalai Lama that says we need to learn the rules so that we know how to break them properly. So if we dive into the code and the code language and we understand the different compliance paths, we break open large ability to have flexible approaches to figure out the most cost-effective way to build homes to meet the intents of the codes, but also not drastically change the way that we have been building, but build houses that are better performing and work over time there. So thanks so much for spending some time with me today. I appreciate it. I appreciate the opportunity to work with you and look forward to our next session. If you want to reach out to me directly, don't hesitate. There's my contact information. And I'll turn it over.
Thank you so much, Robby. Really appreciate this really informative session. I just want to really quick, I know we're running close on time here and need to end at 9:30. But I want to just mention that in the next 2 weeks, we have 2 more sessions. Robby, can you remind me of the name of the next session?
We're going to be talking about the requirements in the code, those things that moved from prescriptive to mandatory to just requirements.
Great. Thank you. So that next session will be next Wednesday, May 8th, same time, 7:30 a.m. to 9:30 a.m. Since we are running short on time, what I'll invite folks to do, if they do have questions that they want to dig into, you can reach out to myself at the town of Crested Butte, or you can reach out to Robby. His contact information is listed there. But just want to thank everyone so much for jumping on and joining us for this session today. And we hope that in the next couple of weeks, we can provide you with more useful information. Let's see, I think if anyone has one quick question, we just have 1 minute left. I might invite them to just raise their hand using the raise hand feature on Zoom, and maybe we can get that answered. But if everyone is good, we might just end now. Okay. I'm gonna give one quick more second for somebody to find that raise hand button. Not seeing any hands, so I'm gonna go ahead and say thank you for joining, everyone. Have a great afternoon, and hopefully we'll see you all next week. Thank you.
Take care.